Right. So to extend this concept to all vectors in the sequence or to all inputs, it's just is very simple. First step, of course, is to compute our attention scores, and we know attention scores, they're calculated by dot products between the inputs. So that's what we're doing here. We're just calculating the dot products for each across all inputs. Here we have a 6 by 6. We know it's a 6 by 6 because we have 6 inputs. So we want it to be 6 by 6, the result itself. Uh, this is manually doing it using for loops for each of the inputs, and then we create j. So it will be I, j, I, j. When I is 1, we then change the j to 1, 2, 3, 4, 5, 6. Now we've calculated the attention scores with respect to 1, which is I equal to 1. Then we move I equal to 2, and then we move j from 1, 2, 3, 4, 5, 6. We've calculated the the attention scores with respect to I equal to 2, and so on and so on and so on. That's what it's just doing in this for loop. Pretty easy, but it's not very efficient. So we can use matrix multiplication. Imagine we are dealing with sequences that are very long. It was going to be difficult. So here we do what is most efficient using matrix multiplication, and that's what we're doing here. Same result, but much more efficient. And then similarly, then we go to step two. Step two, similar to what we had previously, we compute the attention weights by then normalizing the attention scores. That's what we're doing here. We're normalizing by attention scores, pretty much. And this dimension minus one, it's a very good one because it's going to come up later. This dimension minus one just means use the last dimension, calculate this softmax, apply it on the last dimension of the attention scores. So attention scores, there will be something like this. When it comes to dimensions, right? It's like rows and columns. That's what we have. So when we say dimension minus one in Python, minus one means the last element. So the last element here is the columns. So we are saying do the softmax across the columns. So it will do it like this, which means it's actually doing it across the row, because we're calculating on the dimension, which are the columns. As you do it going from column to column to column, you're actually doing the softmax per row. So here we're not doing softmax per row. That's what we did. And that's what we have. And you can verify, and these are the attention weights. So it was actually on this per row, not on, these are the actual results. And then you can get the second row here. We just got the second row, this one here, to see that it actually sums up to 1. As you can see, it does sum up to 1. That's the second step. We now have our attention weights. The third step is just now to do matrix multiplication between our attention weights and our inputs. So attention weights and our inputs. We now get our Z. So this is Z1, this is Z2, Z3, Z4, Z. To check, we know previously Z2 is equal to this one here. And that's it. That's it. So here we've calculated now our our attention or our context vectors in this very simplified as self-attention. Didn't have any trainable weights. In the next video, we are now going to improve or move on to the second version of attention, with second variant, which is the one that is self-attention with trainable weights. So let's see how we are going to improve on this to include trainable weights.